So last year I talked about some of the various things that we use 3D printing for in my group. We're mechanical engineers, but we work very closely with a number of hospitals, including Prince of Wales, which is just up the road from us. Last year we just started doing 3D printing for our vascular access work, and since then it's become a really integral part of the vascular access work. So I thought I'd focus on that and show you how we're using a range of 3D printers and 3D printing techniques to try and improve vascular access. And our main thing is fluid dynamics. We're all fluid dynamics people, but we've moved into a couple of areas as well, just because there's been this kind of need from the work that we're doing. So just a brief intro. The last few talks have all been about bones, so moving back to blood flow. In case you're not familiar with what an AV fistula is, it's to do with when you have kidney failure and you now need to have your blood filtered outside of your body. So in order to do this efficiently, so that you don't need to have your blood being filtered continuously, what is normally created is an AV fistula. So the blood flow that is normally going down generally the radial artery into your hand, flowing around and then slowly coming back up. Often they make a radial cephalic fistula, which is the one we mostly deal with. What happens instead is, so we've got a normal flow rate in the radial artery of say 20 to 30 mils a minute, or in the vein. And then what happens is this artery is chopped off and connected to the vein. So instead of the flow going around into your hand and slowing down, it just turns a sharp corner and comes speeding back up through the vein. So the vein then becomes a place where you can put the needles and get a lot of blood flow coming out to efficiently have the blood filtered under dialysis. So this blood flow is turning a sharp corner. It's going very, very fast. You can see how fast it goes. It's a huge increase from what the vein was experiencing immediately beforehand. And if that's not bad enough, we then stick two needles in, and one of them takes the blood flow out and the other one pushes the blood flow back in. So you end up with this jet flow that's coming in and impacting on the wall. So not surprisingly, they have very high failure rates. And there's a lot of stenosis, particularly occurring in these regions. And we know that this is because of these really unusual blood flow conditions that have happened. And the failure can occur quite early as well. So the way in which our group looks at these blood flow problems, and we look at stenosis as well, which is obviously what this one is we use a combination of experimental techniques and computational techniques. This one is a computational model showing the turbulence in a femoral artery over the cycle. It's obviously not a real femoral artery. This is a idealised shape that we sometimes look at. And this is the same type of vessel with the same type of flow. The femoral artery one is interesting because it goes forward and then it reverses. So from a fluids point of view, we think it's pretty cool. And so you can see the really disturbed flow that happens straight after the stenosis, where you get this jet coming through. So we use a combination of these two techniques in most of what we do to try and understand how the fluid dynamics is then affecting the wall shear stress, which then might affect the vessel wall health. So a few years ago we thought we'd see if we could use fluid dynamics to try and understand what's going on in fistulas and maybe see if we could do something about decreasing these failure rates, because it pretty much sucks already to be on dialysis, and to have to keep coming back and having interventions all the time makes it even worse. So we started making these generic models. This was our fistula that we just kind of came up with from looking at different patient models of fistulas. It's made of acrylic. It was machined in our workshop. It's quite beautiful. It's all nice and clear. We were then able to use our lab to do some experiments on that. But it's a generic model, and as I'll show you in a minute, fistulas are all really, really different. So what we found out from this one was useful, but we thought doing patient-specific models would be much better. These are some of the results we found. They're kind of hard to see here, but these are some of the flow visualization results for the experiments, and we can also do computational results as well. So this is showing wall shear stress. So you can see, for example, the red bits are where we expect that we might get some problems happening. Okay, so we thought we'd better come up with a method for patient-specific models. This is, oh, their heads have been chopped off. These are two of the PhD students up at Prince of Wales Hospital. The thing about kidney failure patients is that you can't get very good geometry. You can't get CT or MRI because they generally can't have that because their kidneys can't filter out the dyes. So all we've really got is ultrasound, and ultrasound is pretty rubbish data generally. And dialysis units tend to not have very much money, and they have these rubbishy little sonocyte machines that you can't get much data out of. We started with the sonocyte. We ended up finding some funding and buying our own slightly better machine, which is a Mindray one, which has really good resolution. We then developed a system, can't see in this image because for some reason it's got shrunk, but there's a camera, a 3-camera infrared system, and we have trackers on the probe where we scan the patient. So for the last about 18 months, we've been going up to the Prince of Wales Hospital every Wednesday afternoon when they have their vascular access clinic, and we scan a number of the patients. And so as Eamon, who's become our mechanical engineer sonographer, scans the patient, me and John sit there with the computers, and the camera tracks exactly where the probe is, and then we're able to recreate a 3-dimensional geometry. That should show a movie. I'll just see if that will run. Yeah. So this is the system in a bit more detail. You can see the little balls on the probe, and this is what happens. We track a whole lot of planes, and then we join all these planes together. Didn't seem to work there. These are the individual planes. Once we join them together, we can make a complete 3D geometry, which it keeps cutting off, but that's that little red bit. Because we know where the probe is in 3-dimensional space. So it means we can get very accurate, quick and easy 3D geometry from the ultrasound. So we've started, as well as scanning just any of the patients that come into the dialysis clinic, we've started also scanning some patients week by week. So we've scanned them before they have fistula surgery. So we get a baseline, which is the blue and the green over here. And then this guy looking like he knows what he's doing is actually one of the PhD students, John. So John and Eamon go into the surgery, they take photos of the surgery, they scan the patient while they're in recovery, and so we get some data immediately post-surgery, which is what this red one is. We've then had a number of patients who've agreed to come back every week, and we scan them every week afterwards, so we can see the longitudinal development of the fistula over time. So we found that we had these quick, easy, accurate 3D geometries of fistulas that haven't really been able to be obtained before. And there were 4 things that we realised we wanted to do with them. Obviously, we wanted to do the CFD, do the computational work, and our benchtop experiments. But 2 other things happened as we were going up to the clinic, which we hadn't really expected. And I'll show you what these are. These are some of the computational models, which are all quite straightforward now. We've got the geometry, so we've run these for about, I think, 120 different patient cases. This is just showing how we need to make them optically clear. This is when we pour in a refractive index match fluid. So because we're using lasers, we need, if the laser sheet bends as it goes through the model, then we won't get a good image. So what we do is we put a fluid in that matches the refractive index of the material. And in that way, the light doesn't know it's going through a different material, and it doesn't know it's there. So it pretty much disappears. So we needed to make accurate geometry. So we needed to be optically clear for laser access, and we need to be able to refractive index match. So the way in which we've done this is we're 3D printing from a wax printer, which is the blue, some of our patient geometries. This is actually a coronary artery. It just happens to be the one I've got the best photos of. So all the bit you can see in the blue, the rectangle is just the frame that it sits on, and this thing's about this big. This is a patient-specific non-scaled coronary artery. And then that blue bit is the actual wax print of the geometry. We then put it into this slightly over-engineered casting box and pour in PDMS, which is just a type of silicon. Once the silicon has set, and we usually just cure it at room temperature because we get the best material properties, we then put it into an oven at reasonably low temperature, about 30 or 40 degrees, and we melt the wax out. That then leaves us with this optically clear model that we can then use for our experiments. This is the 3D printer that we use for the wax printing. As you can see, it's got a very high resolution, so we can print to very, very good accuracy for some of these models that we're making. What I've had one of my students do for the last few months, once we realised that there were a couple of other applications, is to go and find every available 3D printer that we had in the building, that there was across the university. He even sent out to a few different places in Melbourne and in Sydney, and even a couple of places in Hong Kong, and got lots of things made. Because we wanted 2 different types of 3D prints for 2 different applications. So we wanted one that we could just give to the patients, and we wanted one that we were going to use for nurse and surgeon education. And that one we wanted to be really good resolution. The other one, it didn't matter so much. So you can see the prices range from, I think the blue one's the cheapest, it was $1.40 or something. This grey one at the top here, $83. It was all right, but... and also the ones that say UNSW, they're made on our own machines. So the way that Vincent, who's been doing this work for me, has calculated a cost, because we don't, we're just paying for the materials. He's actually worked out how much material we've used and then worked out a cost based on that. So the reason we started making patient ones is when we were up there in the clinic, we found that the patients were starting to ask us questions, and the nurses would introduce us as the engineers. And we think that they started asking us stuff because we weren't doctors, and maybe we were less intimidating. And we realised, and it's also, there's a lot of stuff in the literature about people going onto dialysis just really not understanding what's going on with them. And you can see why this might happen, because a lot of them are getting diagnosed quite suddenly. There's a lot going on, there's a lot of information overload. And so they go and have surgery for this fistula. And we spoke to one patient who actually thought having the fistula surgery was going to cure him of the kidney failure. He thought he was going to have the surgery and then that would be it. So there's a lot of just kind of misunderstanding. And also that we know that people who do understand it more are a bit more prepared for dialysis. Now this is us typically there. John's kind of hidden behind the ultrasound. I'm normally sitting here. So we started showing the patients on screen. This is your vein, this is your artery, this is your fistula, this is the stenosis that Dr. Thomas was telling you about. They started asking us lots and lots of questions. We started showing them the ones that came back the next week, our CFD models, showing them the flow going around. A number of them were really, really interested. As just a side thing, we thought, we'll 3D print one of the models and bring it the next week. The first thing we found when we first printed one, I think one of these ones, is we went, far out it's little, because we were used to seeing them on screen. When we saw how little this thing was, we were a lot more impressed at how the nurses do their job, getting a needle into something this size. But then we also started bringing them along to the patients, particularly ones like these. And we found that, so we started bringing them along and just showing the patients and explaining to them, this is your artery, this is the vein, this is what's going to happen. And the nurses and the doctors started telling us that they were getting feedback from the patients saying that they started to understand a little bit more what was happening. Obviously, we didn't want to say too much because, we don't, we're just there as a side thing. We don't want to give them any medical advice, but we were just explaining from a fluid dynamics point of view what was happening. So we started making it a regular part of our work there was to print out these 3D prints and just give them to the patients if they were interested. Some of them didn't want to know, and I think one of the speakers earlier mentioned that 16-year-old who didn't want to see a picture of a heart. We did have the odd patient who just did not want to know, but most of them were quite interested. So we then started trying to work out which would be the best option. We've had our faithful MakerBot for many years, and this is a MakerBot one. It's pretty rubbish really now. We've recently got a Formlabs one. That's quite a bit better, and we've been playing around with different materials and that. And this year we've got 4 of these, which are they're a little bit more expensive than a MakerBot, but they seem to produce a much better output. And it may just be that they're a newer version. So we started printing a whole lot of different things on those. It's a different one. But you can see the resolution of the MakerBot one is not that great. And this is where we're up to, I think, when I came last year. Since then, we've been playing around making all sorts of different ones. These ones here are Ninjaflex, which I picked up last year when I was here. Someone was using Ninjaflex, which is a flexible material.
You're welcome.
Thank you. May have to ask you later because we're still struggling to get the Ninjaflex to work very well. We end up with a lot of holes in it. It's very porous. But we thought it would be cool to make flexible fistulas, so we're playing around with that as well. So we ended up with this one, which I think is the one I'm holding, $1.74, and the Formlabs one, which is $1.92. And the Formlabs one is a much better resolution. So that's now the one that we're using, which takes a couple of hours. We can do it, for almost no cost, and we can just hand them to the patients. These are ones that I actually picked up. They look like a roller coaster because this is the scaffolding. I picked these up off the Formlabs printer last night as I was walking through the building, which is why we haven't taken them off yet. But we've just started playing around with a clear material. Obviously, if we could 3D print an optically clear material, we wouldn't have to go through that whole process with the wax printing. This isn't quite optically clear enough, but it's getting quite close. So we're getting quite excited about whether we can get something like that, because, then it would make our life much easier. Now, the other final area that we're looking at is, because we were taking these models up and giving to the patients, the surgeons and the nurses started coming in and looking at them and saying, oh, that's really interesting. Oh, you can really see where the stenosis is. So we thought it might be good to make a whole range of them, make some for pre-assessment, make some to show where the intervention might be needed. And also one of the nurses up there, Sue, suggested that we make a range of different fistulas so that she could show any of the new nurses and say, this is how different they all are. I brought a pile of fistulas with me, and I'll bring these to lunch if anyone wants to have a play, but these are all to the same scale. These are all, patient size, and you can see the difference to them. This is a brachio one, so they get quite big. Some of these are tiny ones, so the nurses were saying for them to be able to just see the variation is a really good educational part. So part of what we're doing is putting together a database of all these different fistula geometries with a little patient case next to it, so that we'll be able to give it to the dialysis unit and they'll go through and say, this was a 37-year-old female with, whatever, and any interventions that they've had. For these ones, we want really good resolution. So for this one, we're using the Project machine, which is an MJN machine. One of the big advantages is it melts off that support material, so we don't end up with a roller coaster that you have to chop off, which does leave often a bit of a mess on it. So that's that's not a Formlabs one, sorry. That's the Project. Got the wrong caption there. They cost about $30 or $40 for each one we make because of the materials. So they are quite a bit more expensive. This is just showing some of the range of them. And as I showed just before, the variation in size. Some of the things we've also done is done some pre and post intervention. So this is pre-intervention with a stenosis, and this one is after the stent's been put in. We'd also like to try with the Ninjaflex. One of the things we want to do is make a flexible one and put an actual stent into it, so then the nurses can feel what that's like. So maybe we'll see if we can work that out. So that's sort of our next stage, is just putting together this. We've almost got all the data, putting together this kind of portfolio that we'll then give to the dialysis unit we work with, and if that's useful, then we may be able to send it to other ones. So just finally thanking the great people that we work with up at the Prince of Wales, who were really happy to let us come and invade their dialysis unit and let us free with their patients. And thanks to Vincent, who's one of the fourth year students, who's been making all the models and putting all these beautiful labels on. Thank you.